Okay. So apparently it's time. Okay. Hi, everybody. My name is Denis. I'm a performance engineer at Meta, and my talk is titled Advanced SIMD Algorithms and Pictures, right? We're going to do interaction, right? So if you have any questions or anything, I have the Discord for my chat, for my talk open, right? So Advanced SIMD Algorithms and Pictures, if you find that in Discord, you can type anything in there and I will react to it like while we're talking. It's absolutely not important for us to get through everything. It's just, so it's much better to stay on something you can understand it. Okay. Yeah. So, okay, what this talks about? So first of all, like URL is for slides is posted in the channel, right? And this is for YouTube or something. You can find it there. So like the idea is that there's this technology, SIMD, vectorization. Many of you probably heard the word. If you typed anything, if you ever wrote some SIMD code, do like let me know in the chat. That's pretty cool. Just to have a feel, maybe some people actually know this stuff, but most people don't. And even if they do maybe one or two things. And there is not like one concentrated place you can find all of the algorithms, right? So this is somewhat similar to what you would get in college if there was a SIMD algorithm course, like a sample of that. I'm going to cover a few algorithms. So I'm going to talk about memcmp, copy if, and set of the section and sort. All right. So let's start with memcmp. So memcmp works like this. You have to erase, and we're going to compare the elements until we find the element that is not equal. And then we'll return like -1, 0, or 1, depending on less, equal, or great. So the question is, do you think there is an algorithm in the standard? Like what algorithm in the standard library we could use to implement it? Like if we had to write memcmp from scratch. Anybody have an idea of how to implement this with a standard algorithm?
Sorry, I didn't hear that, but
how would you implement this with a standard algorithm?
Oh, yeah, you just copy a standard algorithm. You use this STD
like
CMP.
I think you can just type in the chat. I think that'd be better, like because the quality will be in the Gather Town chat. Okay. So there are two standard algorithms that can help us. I will move on here, but please to answer questions, like if you can. So there are two standard algorithms that can help us here from the standards library. One is called mismatch, and the other is called lexicographical compare freeway. Right, both of them, like if you look at STL, we could use to implement it. However, that isn't like, and they will do something like this. So it will be like comparison by byte. However, there is an obvious trick to try to optimize it. Like just within the standard, standing within the standard. Do you think you can write better than just comparing char by char to arrays? All right. I'll give 5 minutes to everybody to kind of fully join. So what we can do is instead, we can use int64s, right? So we can compare, let's say, int64s. And in theory, it should work, right? Like there's a little bit of a caveat. What if you have less than 8 bytes worth of things to compare? But assuming that you can deal with it, like int64 should be okay. By the way, because the beginning and the ends of the array might not be aligned to 8 bytes, you cannot just load the int64R. You need to, you can't just interpret cast or anything. You need to do something like this. You need to memcpi. This is how you write an unaligned load in C++. So you do memcpi from the address of 8 bytes. Okay. So unfortunately, compiler doesn't do it for you, and the standard library doesn't do it for you. This is std mismatch. This is something I hacked together using int64s. But by the way, there's some effort at the moment in libc++ to try to make this better. But anyway, this is standard memcmp, which is what we're trying to implement. So you can see that int64s is about 8 times faster than chars. Char compare, which is what we expect, because you're comparing two int64s is roughly the same instruction comparing 1 byte, but you do 8 times more data. And this turns out to be roughly the same idea, except instead of using just 8 bytes, which is what we're doing here, it uses specialized registers that are available on this machine that is 32 bytes. Those specialized registers are called SIMD registers. And so the specialized registers are called SIMD registers. And because single instruction multiple data is specifically designed to deal with big chunks of data. Okay. There are many different ways to try to access those SIMD registers. We're going to be using Eve library. So Eve library, it's on GitHub. It's open source. It's maintained by Joël Falco, Jean-Thierry Lapreste, and me. And it's Boost license, so it's free to use for everybody. However, this is not really talk about the library. This is a talk. If you want to talk about the library, it exists on YouTube. It's called SIMD in C++ 20 Eve of a New Era. Right. And in this library, we have algorithms, and specifically, specifically there is mismatch. Okay, so let's look. It's supposed to be kind of like standard mismatch, only SIMD optimized. So let's look how it does. So this is whatever hard thing with N64s. This ST mismatch, this is Eve algo mismatch. It's a little bit slower on these machines, like it's whatever Intel I have. However, if I look on Apple, it's even faster than the standard memcmp, right? Which is really cool, which we're really proud of. I'm not going to explain why, but we can talk about it afterwards if you want to. All right. So given that we kind of give the same performance about as standard memcmp, we do it correctly, right? It does exactly what I expected. Let's look at how it is done. Okay. So one thing that I mentioned is that I said on this machine, on that machine, right? The spectral extensions, the SIMD extensions, right, are not just universally available. They depend on specific processors that you have, right? And so there are different family of extensions, it's just custom style. This is like all different ones. I kind of was thinking about supporting. Not everything is supported in Eve at the moment, but most of them are. And what I'm going to mention is that it is important which one you use, right? So you need to compile your code to enable the correct, to tell that, oh, okay, you can use this family of extensions because I have a more than enough processor. I'm not going to explain how, but I just know it's important, right? So this is the difference between compiling the codes correctly and compiling the code with just free on my computer. So both of these are still better than just using int64 instead of C++. But this is 2x difference from just 2x difference from just compiling code. So given that we established that mismatch is what we want, in Eve algo mismatch is what we want, let's look inside. Let's see what it does inside. Well, actually, it was a ranges library. So inside of mismatch, it's just going to zip two ranges and do find if or set. We're really proud of that. It took it forever to implement. But it's not really explaining how the algorithm works. So let's look at how the algorithm works in code. This is sort of what it would look like somewhere in the middle of the loop, right? So imagine this is the middle of the loops that you do over and over again when you implement mismatch. So step one, we need a SIMD register. If those are called whites, and so the if white is going to be, on my machines, it's going to be 32 bytes registered. We load both of those, right? So this will load 32 bytes here and here, all right? Then we're going to do not equals. So in SIMD libraries like this, the typical situation is that the comparison is just not just one Boolean, but many Booleans. Matt likes my gut volt usage. All right, so not equal. Not equal returns you not one Boolean, but many Booleans, right? So specifically, this example, 0, 1, 2, 3, 0, 9, 2, 3, right? So the not equal is going to be, the first element is going to be true. And then we have this reduction that says first true is going to return you an optional, right? And it's going to be the 1. All right, but if it were equal, right, if there is no true, then this will be null. And so what will happen most of the time, imagine you load two 32-byte registers, you compare them for equality, they are equal, you go to the next batch, right? So effectively, this is going to be a loop. We load, we do test, then we not much, and then if we don't much, we go plus 32 bytes. Finally, there is like, if we found a match, we just adjust, and okay, this is going to be a mismatch. All right. Cool. Now, how about we have a look at this, and then, like, if you have any questions, like, I will answer those, because this is a bit faster. Okay. You feel free to still type the question if you didn't have time or anything. But I'm going to explain how first true works. Okay. So this is first true with the caveat that there is one family of extensions for RMSP, which is completely different, that has nothing to do with this implementation. But overall, what it looks like. So we have this logical. Logical is a result of not equal, right? And this logical is going to be a some special register. Right? What we want is to find the position of the first true element. So usually there is an instruction to check if there isn't any true at all, right? And if there is no matches, then we're going to do to the next 32 bytes. So this is basically becomes our main loop. Like here, we'll do, is there an any? Not any, go again. Then if there is a match, what we need to do is we need to convert it to a bit mask. Okay, this is some specialized SIMD register. This is an integer. Okay, in E, we call it top bits. Think like one bool is a bit to true or false. In reality, right, this is actually going to be a class, and there's sometimes not going to be just one bit per element, but maybe 2 or 4, but it doesn't matter. Like, pretend that it is one element, it's just a shift, right, to get this right. Well, okay, now, hopefully, people are in chat. How, if this is an integer, how in the C++ standard can you get to the position of the, how do you get this? How do you find this distance? Like, it's okay if not C++ standard. There's a standard way, but many people don't know it. Okay. Masking bit shift, there is a better way to do it. I don't think so. Like, I don't think you can get quite that. There is a special kind of like any built-in method. Yes. Yes. Okay. So the standard was the standard one in C++ 20 compound trading zeros. It's CTLZ, whatever. Like there's an instruction to do it on anything that is remotely modern. If you compile correctly, there will be an instruction to do it. Yeah. So basically, like just to and then this is your answer, right? So let's have a look, just so I'm not lying to you. So this is Intel, right? So move must be on Intel. There is no any instruction really, right? So people go to top bits directly, right? And this is the instruction: go get top bits, right? Then we test top bits. This becomes our any. So like, do we have a bit mask anything? No. And otherwise, this is counting zeros. This is bits count. Well, it's called bits count forward. Doesn't matter, right? So this is kind of like two instructions. Okay. Yes. Now, there is a proposal for standard SIMD. So I'm going to mention it. It's like the default version of it, like there's one that is proposed for 26 is actually not bad. And this is how they do what we do, right? So what we call wide, they call standard SIMD. What we call load, they have a method called copy from. Well, we call logical, they call SIMD mask, right? They have the same not equal operations. And finally, what we call first through, they split into two. Like they have an any of function, and they have a function called reduce mean index that requires that any of returns true. So basically, it is this split. So they do any of, and then they do this one. I am perfectly fine with this API. I think it's quite okay, except I don't like this reduce mean index. I think it's a quite horrible name. The previous version was calling it find first set or something. That I like quite better. Somebody's typing. If there's a question, I'm gonna wait for it. Okay. So if you have any questions, like that's required to go back, it's okay. We'll have time for questions. So let's talk about copy if. Right. So when I first started, you can do copy if, I was surprised. Because copy makes sense. Like copy is easy. You take a big register, you load it, you store it. That's it. How do you do copy? Well, let me introduce you the notion of compress in SIMD program. So what you do is, okay, the standard SIMD, let's talk in the end. So there's a notion of compress looks like this. So you have a register, you have a mask, right? And what it does is it takes the selected elements, right, and it pushes them to the front. Right? And finally, what happens with the rest of the elements, we don't really know. Right? The thing is, this is a notion of compress. This is not really a function compress. Why? Because sometimes this is crazy inefficient. And so in Eve, what actually happens is we have a lot of different functions that has the word compress somewhere in the name. Let me also mention that people on previous iterations of this talk mentioned the word string compaction. I had never encountered that, but I guess that's maybe also how some people know this. All right. So the function from Eve that we want here is called compress copy. It is very similar to just register compress, but it looks like this. So you have two arrays, right? You have a pointer and an output pointer. And then you have a logical mask. Yeah, so such as they say that stream compaction is used to GPU world. Yeah, I'm not like never wrote GPU, so maybe. Right. So they have a logic. This is a logical. This is an input pointer. This is an output pointer. Right. What it does is it takes the elements that correspond to the mask from here and compresses them together in the beginning. And then what it does, it returns you a pointer after the last element return. Okay. Now, have a think. Do you think you can implement vectorized copy if you had this function? So magic function, pointer, logical whatever, mask, right? And then you test, copy if to zone. Okay. So yeah, it should be very straightforward. Just copy, compress copy, compress copy, compress copy, right? You do the SIMD predicate, compress copy. Okay. There are a few variations on the subject. So step one is there is safe, unsafe. So what unsafe kind of does, it allows to write a little bit of extra memory after the last one written. It just makes it much, much faster. The restriction is up to the register size. So it's not going to be basically not relying on specifically at most some number of elements being true. A second one is sparse dense. So the sparse one is when you know that you're not going to write many elements out of the register, right? So like if you, let's say, only like very rare elements are selected, it's going to be better. I'm going to have an example. Let's talk about the interface for a second. So the interface for standard copy if looks like this. First, last output, and I'm missing a predicate. There's a predicate here, right? And what it does, it returns an output iterator. This is a perfectly fine interface for standard copy, no problem. However, there's a problem for SIMD, specifically this output iterator. Because if we just have output, like think about it, you have 1 million elements, and you have 2 elements in the output, right? And it means that you can never use unsafe copy because I don't know how many elements you would have in the output, right? So it means that you would have to use safe, and it practically will kill the whole performance of the thing. I had the chance to ask about this Bryce Leibach, who was at some point in charge of standard unseek, which is an attempt to put SIMD algorithms in the standard library. And he said that the idea there is that standard algorithms, unseek algorithms, are allowed to allocate. So what will happen is if standard unseek is implemented, right, that copy, if it works like it would allocate a buffer, copy if there, and then copy to the output, which is, of course, not awesome, but that's a way to keep the interface. In if, everything is ranges based, so we just have input range, and output iterator. And then, like, basically, I say, okay, so we copy to 2 elements, then the output range is going to be just then I can write 2 elements, let's say. There's a bit of annoyance here. So think about example again. So you have 1 million elements, you have 2 elements in the output. What do you want to happen? What you want to happen is you copy until you have 2 elements copied, stop, do something, then copy more. So what you want is you want here to return where did you stop, right? And this fact, some standard algorithms now do this. However, I just couldn't implement it. Like, this is surprisingly tricky to do with SIMD. So for now, we just return the output iteration. Basically, yeah, it will not write past the end or anything, but you don't know where to stop. Okay. Let's talk about how compressed copy is implemented. There are 2 main variations. One is kind of pure SIMD, and the other is SIMD scalar. So pure SIMD is way too complicated to explain here. There are sometimes there's an instruction just to do it. Main way we do it is this way it was developed by Stack Overflow user Akrit with really tiny lookup tables. If you have BMI2 instructions set, there is a very clever way to do it, proposed by Peter Cardes. I'm just actually curious, type in the chat if you know who Peter Cardes is, like if you encounter Peter Cardes ever. Finally, there's a switch and shuffle developed by Bazan. Well, we have our own version, but there was a proposal by the Bazan Stack Overflow users that is somewhat similar. Surprisingly, like nobody's responding to Peter Cardes. I think he answers most, if not all, x86 questions of Stack Overflow. We really appreciate him. However, the second one with SIMD scalar, right? I can explain. Let's have a look. So you have a one array, you have the output array, and you have a mask. Right. What we're going to do is we're going to convert this mask into top bit. So this is a bit mask. And then what we're going to do is just going to count trailing 0, find the first truth. This is exactly the same as first truth. And we're going to copy that element. Okay, so this one is true, so this one will be copied. Then we clear the last bit and do count trailing 0 again. And that way, copy that one. Right. And if you have very few elements to match, this is a really good way to do it. This is like 1 or 2 cycles of this operation. Going to be really quick. If you think you have a question about this, you can type it. This was separately proposed by Ilya Albrecht and Pierre Cardes. So let's have a look at the benchmarks. Okay, so this is standard copy if. This is no elements I copied. This is all of the elements I copied. This is like half the elements I copied. Does anybody see, and this is just standard copy if there's no SIMD yet. Does anybody see anything weird with this benchmark? Well, 95% is something happening. I'm not sure. But like it looks, what is the worst case when you copy if? No elements copied, half the elements copied, all the elements copied. There's an option all. Any other options? No, I mean 95 isn't just happen. The worst case is half because branch predictor gets completely messed up. Like, so all the elements is copied is fine. No elements are copied is fine, but the half is the worst case. And this is for shorts. You can see it very clearly. Like the difference is crazy. But here is just that my processor managed to remember like the data, and so it doesn't happen. Okay, this is int, so it's half as many elements, it's the same amount of data, but half as many. Let's have a look at how the SIMD version does. So this is a sparse one. This is the one we looked in with first true. Oh, you can see when it's sparse, it does really well in sparse cases, right? For example, here, 5% of element are copied, and it's going to be like 3 times faster. And this is the SIMD approach. So it's not as good at 0 and 5%, but overall it gives you very, very good speed ups. And because it's like kind of just bit tricks and SIMD tricks, there is no real dependency on data, which is also very nice. And you can see that we can have 3 times speed up here, right? And 3.5. And for shorts, where the branch predictor does not get remembered, like the speed ups is substantially crazier, right? So here is more than 10 times win for SIMD approach, right? Yeah, and like whatever, I don't know. 3 times something. Very nice. So just to be clear, right? This code is a drop-in replacement for standard copy if for like 0, for like integers or some cases, and you can get whatever 10x speed up if you like. Right? SIMD is a very powerful technology that's clearly underutilized by it. This is M1. So on M1, the sparse algorithm didn't really perform well, but here you can see there's a 4 times difference. And here, I just really like that for shorts, M1 draws an M. I think it's cute. Okay. What about proposal? So in the proposals, they have a function called compress. As I mentioned, that is not like there are cases where this will not be good, right? This compress function will not be efficient. However, A, they think they can optimize something. B, they have they also like there's maybe possibilities that by the time you get this, so this is not the main proposal one. There is like it's an extra proposal following the first proposal. So 26, 29, your computers will change by the time a little bit, right? Yes, there's already many machines where this is fine and the just get better, or depending on the time. But worst case scenario, you will have to know whether or not you can use it. All right. And with this, I'm ready to go to the next algorithm. We're actually going to do sort, but if you have a question about copy if, that would be a good time to ask it. so difficult. You have no idea what you look like or like how asleep are you. All right. Okay. So let's talk about sort. So sort, unfortunately, like unlike the other algorithms, I don't have an implementation of sort. It's just a lot of work that I didn't do yet. But other people do. So this is everything I kind of read about sort. I'm not going to name everybody. But I'm going to highlight the people I took directly from when we talk about it. So in order to do a sort, we first need to sort a SIMD register. Let's have a look at how we can do it. So the first time I saw this, the earliest mention I find of this is from this blog, 7 Degrees of Freedom, a question of sorts. And this is, I'm going to explain how to sort a register of 2 elements, and then I'm going to wave my hands and it's going to say, oh, this is how we sort n elements, okay? So this is our register. Imagine 2 elements, 5 and 3, it's unsorted. Step 1 is we're going to do something known as shuffle, where we swap the, shuffle is just moving elements in the register around. They're sometimes called lanes. So we shuffle, we're going to swap them. Step 2, we're going to do min and max, right? So min and max, they are vertical, right? So this is 5 and 3 min, 3 and 5 min, right? It's going to be 3, 3, 5, 5. And then we're going to do blend, which is mix elements from the 2 registers together in an arbitrary way. But here we're going to take the first one from the smallest and the second one from the largest. Now the hand wavy part. I'm going to claim that this shuffle, min, max, and blend is enough to sort any SIMD register. I have an implementation of this. It's just fairly difficult to understand for some reason. Like it's not all of code, it's just very confusing code. If you want to know more, you want to look up sorting networks and bitonic sort. Specifically, bitonic sort is the one that everybody's using. And somebody's typing, so I'm going to wait for a question. The SIMD registers all with powers of 2. They are, so I'm thinking. So there were 2 families. One, there was some spec for RMSV that said non-powers of 2, but then they fixed that and they removed it. So there's all powers of 2. On RISC v5, I think it's always powers of 2. Yeah. RISC v5, I don't know RISC v5 very well. Like, I'm not familiar with it very much, but I believe that's also powers of 2. I don't know. In it definitely has to be powers of 2. Let's do quicksort. Now that we can sort the white, let's implement the quicksort. There are 3 components in quicksort. Who can name them? The name components in quicksort. Pivot, partition, very good. So the third one is recurse is not really like, there is something people do when quicksort goes to the very, very end. I don't think you do merge in quicksort, like you just partition. Yes, thank you. You're the first person ever who mentioned this. Insertion, sorry. Yes. So quicksort is exactly like beyond certain type, it is useless to partition. Like, so you partition up to some size, and then you just do search and sort. So, okay, let's talk about this part first, because this is very simple. Like, when we can sort a register, what we can do is we can just partition up to a register size, and then we can sort those little chunks using the algorithm we just said. So this part is done. It's simple-ish. Now, what about pivot selection? If we can sort the register, is there, do you think there is a way? Actually, let's do this. Can you name me a pivot selection algorithm? Strategy, I guess. Random value, very good. SIMD doesn't help you there, to the best of my knowledge. Choose 3 and take the middle. Fantastic. Yes. So if you do that, can SIMD like basic, medium, first, last, middle? Very good. But choose 3 and take the middle. Those are typical ones. Like choose 3, choose 9, right? And then what SIMD can help you with is that can like the process of selecting the middle of many, it can be like vectorized using our SIMD sort. So I take this from x86 SIMD sort libraries that you maybe heard of. It's recently made some rounds. They embedded like the SIMD sort into NumPy, all that other stuff. So the person who did most contributions to that GitHub when I checked was Rafir Tilpulapali. But there are many people to the contribution, so I don't know who to give credit to. Okay. Let's have a look at what they did. So step 1, we have our array. Step 2, we're going to go with some given equal step, right? So that array. Just basically n divided by the number of steps we want to make. Then what we do is this operation called gather, which loads a SIMD register from many places together in one. And we sort, and then we take this middle element. The reason I'm talking about this at all is because I want to talk about gather, right? I'm not sure that this pivot selection strategy is really good, but the problem with gather, right? When I first saw gather, I'm like, this is amazing. It solves all of my problems. You can emulate threads using gather. You can do all kinds of cool things. Unfortunately, it's slow, right? And it's not, there's no magic to it. There's either an instruction or you load everything into an array and then load the registers. Those are 2 things you can do. And even if it is an instruction, you have to do the load, right? And well, okay, so x86, you can do 2 loads per cycle. So yeah, and if you have a cache miss or anything, it's not going to help you. There is no magic load more data fast instruction. So I personally had no luck using gather for anything. I know some people do, but it's mostly like, okay, we're going to take a hit on gather. It's going to be slow, but then we're going to do something clever. Okay. Now I'm going to talk about partition. So partition, I take this from this blog post by Dan Schechter, nicknamed Damage Boys. This goes to 11, like a really long series of articles about SIMD quicksort, really good. And this is the algorithm he suggests. So step 1, we're going to take 2 registers from each side and just going to store them on the stack. We're going to deal with them separately. They don't matter. Okay, so we just want some space. Step 2. Okay, now time to partition. Let's take a register and let's sort this register. And okay, we have a pivot compare. We're going to compare against that pivot, like everything to the left of this is less than pivot, everything to the right is greater or equal than pivot. What we just did is we partitioned the register. Now, this is not a terribly efficient way to partition a register. Like often enough, you can do something similar to what would be the compressed implementations to partition a register. But as a baseline, it's actually not going to, it's not awful to do just a sort. But anyways, we just sort to do partition. So this is partition the register. Now, what we do is we're going to store it. So what we have like some space here. This is like 2 registers of space. This is 1 register of space. We're going to put it, this is just garbage. It's just space. There's nothing there. We're going to put this register here and here. There's 2 writes. And now where we are. Everything here is partitioned. It is less than the pivot. Everything here is greater than the pivot. So we reduced our problem space, right? And this is our space. This is our open space. Now we just need to kind of continue the process, right? So we were here. This was our open space. Now we're here. This is our open space. So all we do is we take this register from the side where there is less space, and then we will have enough space on both sides to put a register. There's a bit of proof to do that, but trust me. Right, so we can take this register now and we sort it, we partition, and go again. This is a tricky algorithm. However, I think if you understand it on the surface level, that's absolutely fine. Even if you don't, that's absolutely fine as well. Oh, I have a Q&A tab. Ooh, let me see that. Memory boundaries. Let's talk about memory boundaries afterwards. So, please put it in chat, I guess, because I can see the chat on my screen directly, and I don't see the Q&A tab. There's a Q&A chat in the gather room. I'm sorry, guys, in the gather room. Like, I'm so sorry. I cannot see that. I can only see Discord. All right. Let's move on. Let's talk about set intersection. Oh, there's a question. What's the question? Or maybe not a question. That somebody's typing. Okay. I don't know. This is difficult to interact with people over the website. I'm sorry. It's kind of tricky. How many instructions is sort wide? I don't know. Like I don't remember. Yeah, I'll struggle to say. It's something called order of log, I think. But we can look afterwards in that bolt if you want. The amount of instructions is not as interesting as how many of them you can put through. We will have an example. What alignment for new empty spaces? Alignment doesn't matter here. Like it is just, we do unaligned loads there everywhere. Unaligned loads are fine. And unaligned stores are fine. We could talk about, there are some performance implications, but they're not bad by any means. All right. We will have an example of instructions for sort for other thing and how we can look at that. Let's talk about set intersection. So I'm going to assume that not everybody is intimately familiar with STL algorithms as I am, which is a shame, and you should be, but okay. So it's kind of what set intersection is. It's one of the merge algorithms, right? So it's like a merge, right? Except you have 2 arrays, both are sorted, right? And what we do is we go one after another through elements, and then we find an element that is equal, right? If this one is smaller, we advance this one. If this one is smaller, we advance this one, right? We find the equal one, and okay, the equal one gets copied to the output. Because it's just arrays, they can be duplicates, right? It's weird to have duplicates in set, but the algorithm allows it. The standard clearly specifies what will happen. We will say between 1 and all of the duplicates will be written. So, okay, we found the duplicate. Right now we advance, and then finally we find the last element and then we write it down. Okay. There are 2 ways you can vectorize it. One is a SIMD scalar approach. This one I came up with myself. I'm not taken from any place. Let's take a look. So we have, let's say we have a smaller array and a big array, right? And then we have our output. What we're going to do is we're going to take just one element from the small array, and like the whole register from the second array. And then what we're going to do is we're going to broadcast. So we're going to take this element and write it into every element of this register. Like that. And then we're going to compare. So effectively, what we're trying to do, like imagine the scale algorithm. You take this element, you compare it against this one, right? Then let's say this one is smaller. You advance, you take this element, compare it against this one. So let's be optimistic. Let's just take this element and compare with a bunch, right? And maybe we can jump with the log. That's the key. So this is what we do. Okay, if all of these elements are smaller than this one, we can just, there's guaranteed no matches, we just jump ahead. And what if there are? Well, let's check if there is like exact match, and then we just copy this to the output. And after we copy it to the output, we just advance this one. Like, that's it, right? So we advance this one regardless of whether or not we copied or not. So that's kind of like, okay, so there was something in here there was something in here that was kind of less. So let's advance. That was greater or equal than that one. Then we can just advance it. Okay. There's a SIMD scale approach. The other one comes from faster than native alternatives for BP2 intersect instructions paper written by Guillermo Diaz-Campos, presumably. I'm very sorry about the names. Okay, so this is how it works. Yeah, we have two arrays, and this time we don't care about their relative sizes. What we're going to do is we're going to load two registers from each one, all right? And then we're going to go through this very expensive operation called has equal in, right? We're just going to just compare every element against every element in here and going to build your mask as true or false if this one has an equal out. Right? And then what we're going to do is we're going to compress copy, right? So we take, we use this mask to just compress copy. Well, we talked about compress copy. This output. This way, we just intersected two registers. Now, all we need to do is we kind of need to now advance to the next two registers to intersect. How can we do this? Well, okay, what about this last element, right? Well, let's find it, let's find it in here, all right? So it's going to be, we could just compare it against all of these elements, and it's going to be like, let's say, bigger than all of these elements and less than all of these elements. And again, because it's SIMD is one instruction, right? Same as we just did before. And now we advance it. And okay, like because it splits this register like this, there is no matches for anything here, anywhere here. So we can just advance up to here. And the same way we can do this element and here we will advance up one. So we kind of, we advance both of them. And ideally, like you can try to prove, especially in the absence of duplicates, you can try to prove that you advance by quite a bit of time, at least from one side. Okay, let's talk about has equal in. So there is no trick really to has equal in. It's, there is no instruction except for that, like we alternative to the native one. That one does it, but other than that, there is no really instruction. So this is the name of the paper had the name of the instructions that sort of does it sometimes on some platforms, but it's very rare. So what we can do, we have one register, we have the second register. Let's just rotate this register. So we shuffle, right? We take this last element, we put it, well, then this first element, we put it, like whatever, the first element, put it last, right? And then we can compare against this one or compare against this one. That way you get, and we're going to do all of them. So we're going to compare against each element against each element. No tricks to it, right? We're going to do equals and we're going to do an or. This is a lot of instructions. Like how many? This is n-1 shuffles, n-1 equalities, n equalities, and n-1 or. However, it's not always a rotate, but it is always one instruction. This is one instruction, this is one instruction. And more than that, this free, if everything goes through code, more than can be executed in one cycle. So the whole thing will be the number of cycles in the register. In fact, in the paper, what they do is they manage, because they target really modern hardware, they manage to merge these two instructions into one. Let's look at the numbers. So this is set intersection. How the benchmark works? You have total number of 20,000 elements, right? It's just, sorry, 20,000 bytes of integers, so it's 5,000 elements. 20,000 bytes. We split them into two arrays, like a really small array on the left and a really big array on the right, and then half and half here, right? This is the difference here is purely branch prediction, right? So on the left, we can tell that we almost always take the element from the right, and here we never know which elements we're gonna take. Let's have a look. So first, there are two. Well, this is a SIMD approach, right? So the SIMD approach is going to be about like a little bit faster here, like by whatever, I don't know, 25%, let's say. I'm not sure that's correct. And here it's about 4 times, 1.5 times faster. The SIMD scalar approach behaves. Sorry, that's this one. This one. SIMD scalar approach behaves remarkably well. So it is like almost 20 times faster here. Like, not quite. And here it's again, even though SIMD scalar is more designed for like one array smaller, the other is bigger, this is still like 4.5 times faster than the standard algorithm, right? The standard scalar algorithm. On M1, the SIMD approach just didn't do anything. However, the SIMD scalar approach continues to perform really well. So this is, I think, 16 times difference, right? 16 times win on the same data. Yeah, and this is like 2.5 times win on the same data. Same, you know. So in the defense of paper people, right? So I think that what the difference between M1 and like Intel is big register size. So this is 16-byte SIMD registers. Here is going to be 32-byte SIMD registers. In the paper, what they did is they used 64-byte SIMD registers. And you can see that the relative performance of the SIMD approach is better with the register size. So maybe, like if we go to bigger register sizes, like they will switch. Like, so it's just possible that this orange one will go over. Okay. All right. Do you have a question about set intersection? I think somebody's typing. Again, I'm busy about the absolute units. What's the time is unit case? So okay, so this is 9,000 nanoseconds, so 9 microseconds. Yeah, and this is 2 microseconds. I don't know. This is again 300 nanoseconds, and this is 4 microseconds. No, it's not for one operation. This is just total. So it's whatever, 20,000 bytes. So 2 kilobytes. Set intersects 2 kilobytes of data. So this is a pure win. Like if you have a place in code where it's set intersection and it's like 9 microseconds, right? If you set intersect in production code 10,000 bytes versus 10,000 bytes, assuming everything is in cache and all that stuff, like you will get a flat 4.5 times win by plugging a different algorithm. Okay, cool. All right. Yeah. Thing. What would be optimal? I'm sorry, I don't understand your question. Okay. So I can say huge thanks to Joel Falco and Jean-Thierry Lapreste, people who developed Eve library with me, and all of the amazing people who share their research online. Like it is like really large work, and I really appreciate that you can just take it. It's really nice. Yeah. So all of the links. So you can find the Eve library on GitHub. You can find the slides. This URL I posted it in the chat. You can find another talk called My First SIMD that I give at London C++ meetup, where I talk about other SIMD algorithms. You can also find the talk about the library, where we talk about the design challenges there and how does the library, like it's hands-on, like all the views and zip stuff and other stuff. And finally, if you want to talk about SIMD, the cpponline clock is amazing. So cplusplus clock is amazing for that, and also the Twitter is nice, but cplusplus SIMD channel I really recommend. It's low volume, it's high quality, and really smart people. All right, and that's it. If you have any questions, I think we have another 4 minutes here, and then we go to Gaza Town. Do you measure memory bandwidth? So there's a question from the there's a question from the memory bandwidth. So SIMD has this problem. I guess not really SIMD problem, but if you process data faster, the speed, the relative delay from memory is going to become more relevant, right? In fact, there's a paper by Alexander Stepanov that I never read. But I saw the abstract. Where they do something like they do some clever compression. So just to the problem is that they loading data from the data is perfectly predicted. There is no problem there, but just the pipeline from memory to CPU, you cannot supply data fast enough. So they compress data they store and then they pocket. So they do more work. They do compression basically on memory data from on the data from just like memory. Yeah. Okay, so there was a questions that I still don't understand. I'm sorry. Like, what would be optimal? What is the time? What do you expect? Actually, I don't get the question. Like, it's a bit of a difficult question. Like, what's the time you will get in production? Really depends on your data. Really depends on the speed. But we had really good time in production, and you can try like replace the strlen with a custom written strlen and see how much it will take. Right? Like how much it will be worse. What's the trade-offs of Eve, Highway, and STD SIMD? I'm just looking how much time we have. We have a little bit. Okay, so standard SIMD is based on BC. It is similar to Eve, but standard SIMD kind of prioritizes so this is the main one. Like I say, in Eve we say kind of like, if we cannot implement something efficiently on some platform we reasonably care about, right? We're gonna go and make really ugly abstractions until those abstractions we can implement efficiently. This is why we have 5 different compressors and they have just one compress, but all of our compressors are really, really good. And his compressor, you have to know, and it's not going to be performance-wise portable. That's the main one. I'm not sure that's a good trade-off. Like for standard library, maybe for sure you have to go with something simpler and rely on compilers more, maybe. Highway is designed around supporting VLS SV. So, oh my God. So basically it is very, what I have seen, and I have seen very little people Highway, so I maybe unfair here, and I'm definitely biased. But what I have seen is that they sacrifice a lot of API convenience of this like a wide format and everything else, all for the sake of supporting vector length agnostic SPE, which is I'm not going to explain now what it is. It's just bad experience overall. And I think we're out of time. Thanks everybody. I'm going to be in Gaza Town in 2 minutes.